towards the intended signal versus the performance in all the other directions away from the intended signal. So the measurement towards the intended signal is the azimuth. So if it's not directly on the bore site of the antenna, you lose some RDF because you're off to the side. So the desired azimuth and elevation angle. So let's say that I'm trying to determine the RDF of an antenna where the desired target is about 1 F layer hop away. So it's, let's say, in northern South America. On 160 meters, the angle of elevation for a signal like that is probably in the order of 20 to 30 degrees. It's not really, really low, and it's not really, really high. So I care about the elevation angles of moderate levels, 20 to 30 degrees. On the other hand, if I'm interested in working the FT5Z-MD expedition, about as far as you can get from anyone in North America, chances are the elevation angles are very low. So you really care about the antenna you're going to use for that at lower elevation angles where the performance of the main lobe, particularly for Beverage antennas on 80 meters and above, is degraded. So RDF is a function of azimuth and elevation angle, which can change depending on what you're interested in, versus the gain over the entire hemisphere. Not just low angles, but also noise coming in from directly overhead as well. So it's all noise and all sources from the entire hemisphere compared to the main lobe pointed at directly at the azimuth and elevation angle of interest. So that's what RDF is. So let's compare a variety of antennas. Down here, chances are everybody in this room is using some of these. These are some really high performance antennas that a few people in this room have. And as we go down this list, this is in order of increased performance. So low RDFs are relatively low performance receiving antennas, and high RDFs are good. Those are high performance receiving antennas that really focus the main beam on the signal of interest, and the side lobe levels at all angles, low angles, and overhead are reduced as much as possible. So let's look at the small loop antenna. I'll show a little more detail about this in a couple of minutes. That has relatively poor RDF. A small loop antenna, sometimes called a magnetic loop, is a very specialized antenna. It is intended for one purpose and one purpose only, and that is to deeply null out local noise, local RFI sources. Magnetic loop antennas, it's a name I don't like, but it's commonly heard by hams, or small loops, which is more accurate. Their very valuable characteristic is an extremely deep null off of both ends of the antenna. It's a vertically polarized null, and it's very, very effective in completely eliminating local noise sources, but it'll only eliminate one noise source. It'd be pretty unlikely you have two RFI sources at exactly the same azimuth. And that very deep null is only a few degrees wide, but it will eliminate that source. But it has to be local, it can't be skywave propagated, and it has to be vertically polarized, which it turns out most local noises turn out to be vertically polarized. But if there's some odd case where that local noise is horizontally polarized for whatever reason, the vertically polarized loop is not going to null it out. Now there's a surprise here. Look at this. A single vertical, quarter wavelength higher or a short vertical, has better RDF than a loop. How can that be? Well, the reason is that a vertical has very, very poor response at high angles, directly overhead. So a loop antenna is actually directive. It favors low to mid angles, and it has very poor response overhead. So it actually is a better receiving antenna than a small diameter loop, except in the special case of local RFI, single source local RFI. A very simple Beverage antenna on 160 meters, 250 to 400 feet long, or a Beverage on the ground, typically 200 to 250 feet long. They have somewhat better RDF, 4 to 6 dB for Pretty short antenna, and a very, very simple antenna. There's hardly any antenna you could ever build simpler than a 250-foot piece of wire with a coax cable and a little transformer on one end and a resistor on the other end. Or you could just lay a piece of wire on the ground, and I'll show you some photographs of those. In terms of performance, the next in line are the small loop arrays. You've probably all heard of antennas like the K9AY loops. There'll be an excellent presentation at the Antenna Forum tomorrow afternoon on the shared apex loop array. An antenna only requires a space of about 50 by 50 feet. And other antennas, they're all similar types, the flag, the pennant, and the U. You can read about all those just by doing a search on Google. Flag, receiving antenna, pennant, receiving antenna, and you can learn all kinds of details about those. What these all share in common is that they're small. They'll fit on all but the very smallest piece of land, about 1/10 of an acre, and they have pretty good RDF, 6 to 8 dB. They have a steerable main beam. Side lobes are down pretty low. Cost is relatively low. Space requirement is small. The next step up is also a pretty simple antenna. It's 2 short verticals, and I'll show you how to build those verticals later in the presentation. They're separated 65 feet apart. They're 25 feet high, so they're quite small. Even if you don't have a piece of land you can permanently put one on, you can install an array of 2 verticals in about 4 hours. And then take it down when you're done with it. So for a de-expedition or a contest weekend, you can easily install it and remove it. And I'll show you how to do that. That's all you need is 65 feet of spacing to put up a pair of these verticals on 160. Or if you want it switchable, you can put up 3 of them and use any 2 pairs. That'll give you full coverage. So it's pretty straightforward, not a lot of space. Kind of next in line is probably the most popular receiving antenna, mainly because it's been around for 94 years. It was patented in 1920. The Beverage antenna. 500 to 600 foot Beverage. It's just a piece of wire supported typically 7 feet above the ground. Quite high performance and really, really simple. There's almost nothing you can do to make a Beverage not work. It's really very basic and high performance. This was presented at Dayton about 15 years ago as a new invention. I'll show you the 1920 patent for this one. Very good antenna. And then a longer Beverage picks up another dB. Now here's a real sweet spot. And for anybody thinking about receiving antennas, this is a relatively compact antenna that offers really high performance. Look at that number. It's right up there among the very best antennas you can build, including an antenna that takes 20 acres. Just a few dB down. A 4-square array of short verticals, about 65 feet on a side. So that's a pretty small piece of land, about 1/10 of an acre. Offers very high performance. I'll show you a couple of alternatives for that. And now we're getting into the high performance arrays. Either for a single direction, you can put up 4 short verticals if you just need to cover, like say Europe, for example. Or you could build a steerable array of 8 verticals. That takes about 1 to 3 acres to install. Tom W3LPL, who was kind of the original inventor of these short verticals, he believes in one of my concepts, and that is you can never have too many antennas. And Tom has a lot of land, so he has these short verticals that perform really well, and he has some of these phased Beverage antennas also. And the very highest performance is, I'm not aware of any ham who's ever built an array like this, but it's actually 3 broadside Beverages, and if you want to make it fully steerable, you need about 100 acres. We won't talk about that one today. So, all of these antennas fall into 3 categories. It's very simple. Loops, Beverages, just a single piece of wire or several pieces, or arrays of short verticals. 3 categories. Some of the loops are very small, and I'll show you how to build one if you're interested. And the remaining loops are typically 10 to 20 feet in diameter. The shared apex loop array that'll be discussed at the antenna forum tomorrow and that you can buy is just slightly bigger than that. And then beverages of all sizes. And short verticals are typically on 160 meters. They're 25 feet tall. So they're quite practical. I don't think I mentioned at the beginning of the presentations that all of the dimensions I'll speak about, so I don't have to keep scaling antennas from 160 to 80 to 40. All these antennas will work on any of the lower bands. All the dimensions I'll mention here are for 160, but if you're interested in 80, you can just divide those dimensions in half. So you can build a really good 80-meter receiving array, only 35 feet on a side. You can also scale these same dimensions to 40. But I'm not going to go through all those dimensions as I speak about this. So let's start with the simplest antenna of all. This is the so-called magnetic loop. It's just a small diameter loop. It can be as small as about 3 feet in diameter. It's excellent for nulling a single source. It's also excellent for locating RFI. This is a great tool to have in your tool bag. If you're having RFI on the low bands, it can be kind of hard to figure out where it's coming from. But a small diameter loop that you can build on your workbench in about 2 hours is an excellent way to try to determine the location of an RFI source. That can then cause a neighbor to fix an electric fence or get the power company to fix a problem with a power line or whatever the source might be. It's kind of your job to find out where it is. I don't think it's reasonable for us to expect public utilities or a farmer to figure out which part of his electric fence is a problem, but we have the tools and knowledge to find the source, and this antenna is an excellent way to do that on 160 or 80. Small diameter loops have a very broad figure 8 pattern for vertical polarization only. They're omnidirectional for horizontal polarization. So a small loop has very, very deep nulls off the end for vertical polarization only, which means that for skywave propagation, they have no useful null at all. And the reason is that for ionospheric propagation, the polarization is constantly changing. It is rarely purely vertical. So the deep null that's present in a small diameter loop when you're dealing with signals that are coming in from the ionosphere is totally eliminated. No useful directivity. If you have a small diameter loop and you tune in, let's say, a broadcast station at the top of the broadcast band at night that's coming in from the ionosphere away from your local area, you turn the loop, you'll see no effective change. But then if you tune in a local broadcast station within 10 miles of your home, for example, and you turn the loop, you'll see the null is still there. So this is a very specialized antenna for RFI location and RFI suppression in the local area. Like all loop antennas, they require very careful attention to isolating the loop from stray pickup. You want to be sure that the loop is picking up signals only from the loop, and not signals that are coupled in from the coaxial transmission line going from your receiver to the loop, or from a power source that might be going to a preamp at the center of the loop. So isolation is really important. If you don't know how to do this, you can learn how to do it on a lot of the websites that tell you how to build loops, and I'll show you an excellent one on the next slide. There's hardly anything you can build simpler than this. Here's the website at the bottom of the page that shows you where to go for the details as to how to build it. You can buy, this happens to be copper tubing. You could build it out of heavy wire. It's 3 feet in diameter. There are actually 2 loops. For some reason, the people in the hobby that use this, they call this thing a coupling loop. Well, that's not what it is at all. In our people that build Yagis use the correct term for this. This is actually a hairpin. The only thing that does, there's one loop here, and the small loop is soldered to the open connection. And all it does is raises the impedance at the feed point of the larger loop. So this doesn't have to be in a loop shape at all. If you attempted to receive signals on this loop without some mechanism to increase the impedance at the feed point, the signal levels would be extremely low. So this just raises the impedance. You could replace this with a little coil, just like we do on our Yagis. But for some reason, this has gotten a totally fictitious name of coupling loop, which it is not. So all that's involved in this is 2 pieces of tubing or 2 pieces of wire soldered together at the feed point and a capacitor to resonate it on the frequency of interest. It's a narrowband antenna. And a transmission line that's decoupled that goes to your receiver. That's all there is to it. You can learn how to build it right here. But it's a very specialized antenna, but really tiny. And look at the 3 dB beam width of the main lobe, 160 degrees wide. And the deep null is only a few degrees wide, but only for local RFI. So let's look at another class of small antennas. And there are many of these out there. We'll just look at a few. You can learn about all of them on the web. But we'll look at a few of the very popular ones. K9AY loops. I'll show you a photograph of one. It's about the smallest of the steerable loop arrays. Only 25 feet by 25 feet and only 25 feet tall. So it takes very little space at all. Has reasonably good RDF. Notice its beam width is quite broad, 120 degrees. It's a little bit broader than a Foursquare for anybody who's used a Foursquare. Foursquare has a broad pattern off the front, and so does this antenna. A little bit better performance is this newer shared apex loop array that will be described in the antenna forum tomorrow. The biggest difference is that its beam width is a little bit reduced. It's about 75 degrees wide across the main forward lobe of the antenna. And this is also a pretty small antenna, about 50 by 50 feet, and it's also 25 feet tall. And a general comment again about loop antennas is all of them without exception produce low signal levels, so you need a preamplifier and you need to pay attention to decoupling signals arriving from outside of the loop. So let's look at a little bit more detail. You can purchase the K9AY loops from Array Solutions. There's a website. Or you can build them yourself. It's not difficult. The most critical component is the preamp. Switchable in 4 directions. Pretty good RDF and a very, very small space. Does anybody have one of these antennas? You do. Tell us a little bit about it. What do you think? Somebody who's got one. Yeah. Depends on the angle of arrival of the signal. Who else has a K9AY loop in the back of the room? Okay, so the performance is variable. In this corner. I've never used the K9AY loop, but the comments we've heard are not uncommon, that the performance varies a bit. But this is a really tiny antenna. So let's look at the next one. This is the shared apex loop array. You can buy this also from Array Solutions. Does anyone have one of these? No, but there's quite a few that are out there. And the experience is, from the people I know that have them, is about the same, that the performance varies. Sometimes it's surprisingly good, sometimes a little disappointing. But keep in mind, this is a very small antenna also. And unlike the very small so-called magnetic loops, these provide directivity for ionospherically propagated signals, unlike the small loops that cannot do that. Oops. No radios. No radios. But we heard someone say for the K9AY that they found it to be helpful to put a ground wire under it. Yeah, okay. So it stabilized it, I guess. Okay. Okay. So let's move on. Beverage antenna. Does anybody have a beverage antenna in here? Yeah, quite a few. It's a fabulous receiving antenna. It's just about impossible to do anything wrong. It's probably the simplest antenna you'll ever build. It's no more complicated than a dipole, and it's only 7 feet high. The patent application was filed in 1920 by Harold Beverage. He did the development of this antenna at the end of World War I. And what was the reason for that? During World War I, the Germans cut all of the telegraph cables between North America and Europe. The only way to communicate between North America and Europe prior to that, was by cable. And then this guy named Marconi came along. And initially he started with ship-to-shore radio. We've all heard of the Titanic disaster, for example. But then realized his dream that he could use radio to communicate across oceans. Well, by the time World War I came along, he had not only gotten to the point of doing experiments, but he was starting to build systems that could communicate fairly reliably by radio across the oceans. Well, how did he do that? Nobody had discovered HF radio yet. The only way they knew how to communicate across the oceans, just prior to and during World War I, was with massive transmitters, hundreds of kilowatts. So that the transmitters in use at the time were Spark or Arc, which is a little bit different, or during World War I, 300 kilowatt motor generators operating at 24 kilohertz, feeding antennas that were 500 feet high, 300 feet long, 300 feet wide, 500 feet high, 300 feet long, and almost a mile long. Now, could you imagine if no one had discovered HF radio, if we were still communicating with those kind of systems? Well, and the even bigger problem. So the engineers of that period knew how to build things big. They proved that, and you can still visit some of these old sites today. They really know how to build big things. What they didn't know how to do was to build receivers and receiving antennas. And this guy named Harold Beverage came along and solved one of these big receiving problems in World War I, and he did it with the Beverage antenna. And the way he did that is he found a pretty smart engineer. So building a really long, on those frequencies, a long antenna is measured in miles, not feet. So he laid a piece of wire in a sandy, dry area for several miles, put a receiver at one end, and much to his surprise, found out it was directive off the end of this wire laying in the sand for several miles. He could hear the several hundred kilowatt transmitter in Europe much better than he could on any of the other antennas they had at the time. And he continued to develop it, and to make a long story short, came up with the thing we would recognize as a Beverage today, with a matching transformer at one end and a resistor at the other end. His was miles long. It was operating at 40 kilohertz or so. We're at 160 meters, so we're only dealing with maybe 500 feet, and his were dealing with antennas that were long, that looked like a telephone line at the time. 1920. Quite good RDF with a Beverage. A short Beverage on 160, it's got useful RDF. The very popular lengths around 500 feet or a little longer, about 10 dB. It's very good. And if you have room for something up to about 900 feet, really good RDF, about 12 dB. And I'll mention, there's a limit to how long you can make these antennas and have them consistently improve. If you make them longer than about 900 feet long, the performance is often degraded. And why is that? Seems strange. Why wouldn't it keep getting better? It's actually not loss. No, that's not. Does anybody know the reason why they degrade? Out of phase. That's exactly right. The Beverage antenna, because it's so close to the ground, has a slow velocity factor. Not as bad as, but similar to coax cable. So when you make the antenna too long, the signals coming that are arriving at the antenna towards the end are in the wrong phase relationship with the signals arriving closer to the feed point. So there's a limit to the length of the Beverage, and on 160, it's about 900 feet where things start to degrade. But not many people are worried about that. And here's the Beverage on the ground. There's a really good website that describes how to build these. This is a good choice where, for whatever reason, you can't put up a Beverage. It's just a wire literally laying on the ground or just a few inches above the ground with a small transformer at the feed point, a resistor at the far end. And it produces pretty good RDF for an antenna that's pretty much invisible. Some people have been known to put these out across the neighbor's front lawn at night, or to run them across the street at night. There's a whole variety of creative things you can do with an antenna that can't be seen. So this is a useful thing to have in the tool bag. Roughly straight. Roughly straight, yeah. No, Beverages do not have. I'll make a couple of comments. That's a really good question. Make a couple of comments about Beverages. They do not have to precisely follow the terrain. So a lot of people don't have terrain that's absolutely flat. So if the terrain varies in elevation, the Beverage should roughly follow the terrain. It doesn't have to precisely follow it. And if there are obstructions, the Beverage can roughly point in the direction of the signal of interest, but it can deviate from that by probably 5 or 10 degrees. It should generally point in the direction of interest. There are two popular forms of the Beverage antenna. I'll show you the other one in just a moment. There's a single wire version which will cover one direction. There's a two-wire version, but it has nothing to do with the folded dipole other than that it has two wires. So there's a one-wire version and a two-wire version. The one-wire version is dead simple. You could teach a primary school child how to build an antenna like this, and he would build it and it would work. The other ones are a little more complicated. But a child could build this antenna, he could build the other one. I'm sorry, I only heard part of your question. For the Beverage on ground, it can literally be on the ground. You can make small bends. If you deviate from a straight line, it's going to degrade the side lobe performance of the antenna. But if that's the only thing you can do, it's very simple to experiment with. This is a very easy antenna. So if you're not sure, it's not going to take very much time to try it and see if it works well. You're not going to invest but a couple of hours to try to put one of these up and see how it works. So rather than me standing up and saying, yes, it will work, or no, it can't possibly work, this is an experimenter's dream. It's really simple, and you haven't committed a lot of expense to trying it. So give it a shot, and maybe it'll work for you. But I think the basic answer is if the deviations are relatively small, and on 160 relatively small means 10 or 20 feet, it doesn't mean inches or a foot or two, it'll probably work fine. Two-wire Beverage, also very popular with hams, patented 1921. In exactly the same form we would recognize today, a transformer at both ends, so-called reflection transformer at the far end, matching transformer here. This particular version is one that more hams should use. What they did in this 1921 version of the two-wire Beverage is they brought both signals back to the receiver. And then at the receiver, they varied the amplitude and phase relationship of the two signals, and they could steer the null. And I'll show you a device at the end of the presentation that will do that. So if you've got a two-wire Beverage, a nice simple improvement, instead of bringing one signal back, is to bring them both back, and you can do null steering easily.
Same length though?
They don't have to be the same length. And I'll show you how to solve that problem too. Doesn't matter. So let's see if we can learn anything else from the 1920s.
Right. These are close together though, right? It's in black. They're within a foot of each other or something.
They have to be able to operate as a transmission line. The way these antennas work is in one direction the two wires are in phase, so they operate as if they were a single wire. So in that case the spacing doesn't matter. But in the opposite direction, the two wires are actually being used as a transmission line to bring the signal back from the far end. So there it does matter. And on 160 meters space, I don't think you'd want the spacing to be more than about 2 feet. That's probably the maximum. The minimum, there is no minimum. It can be a twin lead wire and it would work fine. So anything from a fraction of an inch to 24 inches is fine for the transmission line performance requirement for this antenna. At Dayton about 15 years ago, at the antenna forum, someone stood up and talked about their new invention, the staggered Beverage pair. They didn't know that it was patented in 1927. It was a great invention. Hams had forgotten about it. And it became popular, not because anybody discovered the patent, but because no one was using it. So it was a great thing to present at Dayton. And it's a very simple antenna. It's two Beverages, one here, one here. This drawing comes out of the patent. They're staggered 1/4 of a wavelength. So on 160 meters, one Beverage is sitting about 125 feet forward from the other Beverage. And this spacing between them is about 35 feet. It's not critical. The main difference is they're staggered, and this improves the RDF by a couple of dB. But the very important thing that it can do is if instead of doing the beam forming right at the antenna like they do here, if you bring both feed lines back to the receiver, you can steer where the null is. So that can be helpful. So you can build it two ways, like they did in 1927 with a fixed delay line, or you can bring both feed lines back to the receiver and do the phasing of the shack. You can find a description here. They're called echelon Beverages on W3LPL's website. Very simple antenna, very effective. Well, let's make it even bigger. So we're going to use 4 Beverages. Patented 1927. These antennas were developed for the first transatlantic telephone system. First transatlantic telephone system was done by radio. And it was done before HF radio was very well developed, so they did it at long wave. These antennas were miles long, about a mile wide, several miles long. And this particular antenna was built in Maine on the Canadian border, right where Interstate 95 crosses into Canada. The building where the equipment was is still there. I visited that building, and the basement is all completely lined in copper. I'm not sure the copper is still there because the price of copper has gone way up since the time I went to that building. But that entire basement was completely lined in copper where all the electronics was. All vacuum tube stuff back in those days, of course. So this has really good RDF, but this is a big antenna even at HF. If you're going to build an antenna this big, the Beverages are probably going to be 800 feet long. They're staggered a quarter wave, so the distance from here to here is about 1,000 feet. And they're going to be separated about 400 feet here. So the dimension of this array is about 1,000 feet long and about 400 feet wide. Pretty big antenna. But you get a couple of dB of RDF for your trouble. But there were more compact ways to get RDF like that. And this only gives you one direction. So you need 1,000 feet by 400 feet, and it only covers one direction. So you better have a lot of land to cover and a lot of time to cover all the directions. Well, there's another way, and I think we have Tom W3LPL to thank us for that. Yes, before. Yeah. Oh, there's a lot of ways to bend wire. And I'm sure if you go onto Google and look up slinky beverages, you'll find articles about that topic. I've never used them, but I know KM1H has used them, and he was happy with them. So that's a slinky beverage. Does anybody not know what a slinky is? You don't know what a slinky? Oh, you know what a slinky is? Well, if you can picture a rope, and you run the rope through the slinky and you extend it out and you solder several together so they run for several hundred feet, it winds up being a beverage that's made out of a continuous coil of wire. Yeah, that's the claim, that it reduces the length. I've never used one myself, but I know people who say they've used them with good success, and I have no reason to doubt it. So that's another way to bend wire. And there's a lot more ways to bend wire too, and I'm not prepared to talk about all of them. So let's move on to short verticals. And this is where the payoff really is in the next generation of antennas. The idea of using verticals for antennas is certainly not new, but you cannot go back into patents, unlike beverages, and find patents for short verticals for any use for receiving going way back. They just don't exist. This idea, as far as I can determine, originated in the ham community with W3LPL and maybe some other hams of that era. There are two types of short verticals that are very effective for use in high RDF receiving antennas. Two fundamentally different types. One is high impedance, and everybody's seen the advertisements by High Z, I'm sure. They make a line of antennas sold by DX Engineering. And there's another very different approach to building a vertical. It's a more conventional approach that's low impedance. And I'll show you some photographs on how you build a low impedance vertical. The biggest difference is for the high impedance verticals. You don't need radials, and for many people that's important. You don't need any umbrella wires to help to resonate the antenna, because the high impedance verticals are non-resonant, whereas the low impedance ones are. And the other big difference is the high impedance verticals need a precision high gain amplifier. The amplifier has to provide the arrays of, you have a high gain amplifier at the base of each vertical. And each of those high impedance amplifiers have to provide the same gain and the same phase delay through the amplifier. So all of the amplifiers in the array have to be matched. It's a difficult project for most hams to undertake. Most of us don't have the laboratory equipment to build and test and verify that all of the amplifiers we might build are exactly the same. But you can purchase the antenna that has the high gain amplifiers that are matched. But there's also some bad news. When you have lightning strikes and other things, it changes the characteristics of the amplifiers. So sometimes you might have to go back and test the amplifiers anyway to see if they're still working the way they were originally. And another constraint of this array, these high impedance verticals cannot be installed near other objects. They have to be well away from trees and buildings. And the reason is that it affects the performance of the different verticals in the array. It affects the amplitude of the signals received, and to some degree the phase, and significantly disrupts the performance of the antenna. So before you think about putting up a high Z array, it's important to think about where you're going to put it, so that each of the verticals is in an environment that's about the same, as close as you can to being in the same environment. You don't want to put up 4 high Z verticals with one sitting immediately next to a tree or one sitting immediately next to a building of some kind. It will disrupt the performance of the array. You have a question?
Can they be installed over an existing radio field?
I don't know anyone who's tried that, but it's not apparent to me why there would be a problem. As long as the radials are not elevated. If the radials are on the surface of the ground or buried, it shouldn't be affecting the signals that are arriving at these elements. So it should be okay. But I can't guarantee it because I've never tried it. But I can't think of a reason why it would be a problem. Yes, John.
W3XY. What about a tower within the perimeter further than 10, 15 foot?
That's a very good question. What about a tower close to the array? That's a more complicated question. How large is the tower? 60 feet might not be too bad. The problem is a different problem. If the tower is very close to these antennas, it affects the amplitude of the signals received and makes them a poor element of a phased array. But if you have a tall tower, close to a quarter wavelength high, so on 160 meters, your tower is much shorter than a quarter wavelength. So the re-radiation from that tower is receiving lots of 160 meter signals all the time, and just like any other parasitic element, they get re-radiated. But that antenna is short enough that it might not be much of a problem. Might not be. Putting one of these arrays close to it isn't what you prefer to do, but it'll probably be okay. It's probably going to degrade the RDF somewhat. It's not ideal, but it's probably not disastrous either. Pete, did you have a question?
Yeah, what's the distance from nearby conductive objects related to the frequency that you're receiving on, or is it fundamentally just sort of square law?
Pete, I honestly don't know the detailed answer to that question, but I do know some of the members of our radio club who've installed these high Z arrays and have made the mistake of putting them close to other objects, and they had trouble and contacted the manufacturer, and they said, "Oh, don't do that." It apparently affects the impedance that the preamp sees and some other things. So they basically tell you, that's exactly what they tell you in the instructions. Keep it more than 10 feet away from other objects. So, all the way in the back of the room. I only heard a few of the words. Can you try that again, please? Well, his high tower HTs are a quarter wavelength long, so they are by no means short. Those verticals are 60 feet tall, so that is in a completely different class. I'll just briefly mention his array. It works really well, but those are full-size antennas, and it's a classic case of trying. He built that antenna before these receiving antennas, before the true potential of these receiving antennas was well understood like it is today. So like most four-square arrays, it was built as a compromise between transmitting performance and receiving performance. You try to achieve both, and you achieve both pretty well, which he's done. But what we've now discovered, and many of us have implemented, is we can now build transmitting antennas that are optimized for transmitting, and we can build receiving antennas that are highly optimized for receiving. And we don't have to strike this compromise between the conflicting requirements between the two applications. So now you'll find the very best stations, including Tim's station, now have highly optimized transmitting antennas to make your signal loud. I don't care about receiving anymore. And we have very highly optimized and simple to build receiving antennas that are much better in performance than any transmitting antenna could ever be. So the world has kind of changed as a result of some of the work that WHJI did and some of the work that Joel, W5ZN, did in popularizing this antenna. It's gotten a lot of interest. So let's look at a small array built with these high Z verticals. And you can buy this antenna. There's the website. You can leave your credit card with K3LR and he'll have one on your doorstep Monday. No umbrella wires, no radials, 80 feet by 80 feet. High gain amplifier at the base of each vertical. Switchable in 4 directions. The beam width is about 100 degrees. And look at that RDF, about 12 dB. I highly recommend for people that build these, don't use the compromise spacings. They recommend spacings that are optimized for the band of interest. If you're going to go through the trouble of putting these up, I think it's worthwhile, in my opinion, to get the best possible RDF on one band rather than getting pretty good RDF on 2 bands. But you can do that if you wish. Receive only. Right, these are not transmitting antennas. Low impedance verticals. They achieve the same tremendous RDF of the high impedance verticals. Unlike the high impedance verticals, they're easier to build. Doesn't take very long to build these. They're 25 feet tall. They require a modest number of radials. I use 8 70-foot radials, and they're in an environment that needs good performance from the radials. Some of my verticals are in a swamp, and some of the verticals are several feet higher on dry land. And it's important that you have enough radials so that the feed point impedance is about the same. I found with my antennas that 8 70-foot radials was adequate. They are randomly laid on the ground. They're not pulled tight. They're not buried. They're just laid on the ground, and that's perfectly okay. I don't think there'd be any benefit at all to making them straight. Or you could use a larger number of short radials. The version that I use uses 4 25-foot umbrella wires. I'll show you a photograph of the antenna a little bit later. It's really simple. Joel's website shows practical details, W3LPL.org. If you don't have room for the umbrella wires, you could lengthen the height of the verticals to about 35 feet. And you don't need the umbrella wires. The performance is only very slightly degraded. You can use as short as 65-foot element spacing in a 4-square array. Smaller spacing than that is really impractical unless you have precision instruments, because the equal amplitude and phase matching becomes extremely critical with small spacing. So unless you really can't get at least this much spacing, and unless you have really good lab instrumentation, I don't recommend trying an antenna smaller than this. No need for amplifiers. They are not needed. These antennas have about the same sensitivity as a Beverage. Some people find it convenient to put an amplifier in so their signal levels are about the same as a transmitting antenna, but it is not required. Not needed at all. They're very tolerant of nearby objects. You can put one of these antennas in a tree if you need to. You can put it on the side of a building if you need to. Now, if there are electrical circuits and other things in the building, it can cause problems. But these antennas are very tolerant. So there are kind of 2 choices here. Low impedance antennas with a small number of radials, no amplifier, very tolerant of nearby objects, easy to build, no need to purchase preamps. The cost of the system is significantly less. So you have to decide which works best for you. So let's look at a couple of arrays. IV3PRK built a small 4-square of low impedance verticals, 25-foot verticals with umbrella wires. He used a small number of radials, 65 feet by 65 feet, easy and inexpensive to build, and his website describes it. He had some difficulties with the performance of this antenna, probably because he had a number of really nearby RFI sources. He's in a fairly small location, so he had mixed success. But it was, and I believe his conclusion is pretty firmly that it was just the other nearby antennas that were re-radiating into this array. It's difficult to put up really high performance receiving antennas when you've got other objects nearby that are adding signals into the array that you don't want to be there. So let's look at a really high performance array. Now remember, earlier in the presentation we talked about how to build a very high performance array with beverages. And it turned out to get this kind of performance number, we needed about 100 acres to cover 8 directions. Well, this is the high Z version of a very high RDF receiving antenna. It's 200 feet in diameter. Not too bad. It's about 1 acre. So with these verticals and about 1 acre of land, no radials, you can get incredibly high performance. Definitely when you are trying to get very high performance receiving antennas, you don't want to put this antenna near towers. You don't want to put it near power lines because you're going to lose some of that RDF, and it's hardly worth the time and trouble to put up an antenna that has 3 or 4 dB of an advantage and then lose it because of a nearby tower or a nearby power line. So this really needs to be several hundred feet from nearby objects, otherwise it isn't worth the effort of putting it up. But it's pretty straightforward. No umbrella wires, no radials, 8 high gain amplifiers, one at the base of each vertical. And its performance is, if you ever use an antenna like this, it's just like using a large 5-element Yagi on 20 meters. Turn this antenna, the increments are every 45 degrees, and I've described my first experience using one of these on 160 meters. There was a de-expedition in the Caribbean, and propagation on 160 was really good that night, and he had a pile up from all over Europe. And my 8-circle array, mine happens to be passive, but the performance is the same as this. It's oriented such that in one direction it points at, it's offset from 45 degrees. So in one direction it points at 25 degrees, and in the other direction it points at 70 degrees. So I could, if I turn to the 25 degree direction on the 8-circle array, I was hearing all the Scandinavian signals in Europe calling this de-expedition. And if I switched to the other direction, I heard all the stations in Yugoslavia and Italy and Spain that were calling the de-expedition. It was amazing to switch between the two, and you heard 2 different pileups, just like you would on 20 meters with a large Yagi pointed further north to Europe or closer to east. It's just amazing to see the performance of these things. I don't know why I waited so long to build it. And this is the passive version. Let me describe. This is one of my verticals, and I'll describe how I built mine. It's a 25-foot vertical. There are 4 25-foot long pieces of wire. Mine happened to be number 14 electrical wire. Nothing special about it. Terminated in a ceramic insulator. There's a short piece of rope here, and then it terminates in a 6-foot high fence post. Why a 6-foot high fence post? Because I've got deer in the area, and if I had just a stake in the ground, like a tent stake, this antenna wouldn't last more than a day. So instead of bringing the rope down to the ground, it goes to the top of a 6-foot fence post. There's no need for these antennas to put them, you don't need a foundation. It's completely unnecessary. Mine mounts on a 2-foot long piece of rebar. But I'm sure there's a whole bunch of schemes you could come up with. You just need a foundation you need something to mount the antenna on that's just strong enough so that it won't sink into the ground or fall over. Because you've got the top loading wires that are supporting the antenna, so you don't need to worry about the antenna falling over. So there's no need for a foundation. So it's just that simple. At the base of this antenna, these low impedance antennas work best when they are tuned to resonance. They work well even if they're not tuned to resonance, but they work best when they are tuned to resonance. And all that's in the little box, and you can learn the details here at Joel's website, but all that's in the box is a little inductor, 28 microhenries. It's the size of your fingernail. Remember, these are receiving antennas. And the base feed impedance here, because the radial system is sparse, the base feeding impedance is about 20 ohms. Almost all of that is lost in the sparse radial system, just 8 radials. Well, I want to match this to my RG6 coax at 75 ohms. So what's the easiest way to match 20 ohms to 75 ohms? It's called a 55 ohm resistor. See, on 160 meters, 45 dB noise figure is a sensitive receiver. And if you've ever used a full-size transmitting antenna to receive on, you know the first thing you do is put a 20 dB attenuator between your receiver and the antenna. You've got to get rid of all that signal. So there's no reason to make this matching network anything any more complicated than a 75-cent inductor and a 55 ohm resistor. That's how you match this vertical to a 75 ohm cable. The whole thing can go in a little tiny box. And with 8 of them, 13 dB of RDF. So we're getting near the end of the presentation. This is the DX Engineering NCC1 controller. This allows you to take 2 receiving antennas. They should be vertically polarized in order to do null steering in your shack. You can also use this device with a 2-wire beverage to do null steering of the beverage. You can also use this device with an echelon beverage. It's very handy to do null steering if you have RFI that's popped up or just for general experimentation. And these controls are very easy to use. They'll compensate for any difference in transmission line lengths. So this is it's not an inexpensive device, but its performance is fabulous. And the last slide is this receiver. The Elecraft K3 is absolutely unique. If you purchase the second receiver, it's exactly the same performance as the primary receiver. It's phase locked to the primary receiver, and listening to 2 widely separated vertical antennas through this receiver is just magic. The sensation you get, usually in my station, we use the K3 with 1 receiver on the transmit 4 square. So we know that's a pretty good receiving antenna, but not ideal, but we have it. And the other receiver connects to the 8-circle array. And if they're pointed in the same direction, the sense you get is that the signal is drifting from the left ear to the right ear or kind of in between. And that's exactly what you hear. Sometimes what we'll do using this receiver is we'll point one antenna in one direction and another antenna in the other direction. And as you tune the band, you'll hear some signals in your left ear and some signals in your right ear, depending on whether they're coming from Europe or the Caribbean. So it's a very valuable receiving tool. So that's the end of my presentation. We've still got 20 minutes for questions if anybody has any. All the way on the far side there.
Paul, W3LPL, you talked about dimensions being for 160, but they could be
Yeah.
changing the dimensions. Are any of them good for multiband? In other words, the 160 can use on 80?
The Beverage, yes. See, somebody said Beverage, so you paid attention. So you get the gold star for the day. A Beverage is a marvelous multi-band antenna. Its performance extends across multiple bands. But these vertical antennas, not so much, because they all depend on the physical separation of the verticals for their excellent performance. With the high Z antenna, the high Z verticals, you can use their compromised dimensions to get pretty good performance on 2 bands. I don't really like that answer, because I'm going through all the trouble to get a really good receiving antenna, and now somebody's telling me I can build a compromised antenna that will cover 2 antennas pretty good. So yes, the high Z antennas will cover 2 bands, pretty good performance. My preference is to build that antenna and build it optimized for 1 band. So, and the low impedance verticals are definitely for 1 band only.
Can you build a low band for just 2 directions instead of 4?
Let's go back earlier in the presentation. I think I can get there here. Yes, let's look here. Let's look at this really sweet spot right here. Let me remind you of this. 4 square vertical of short verticals. So this array has 4 short verticals, either the high Z verticals or the low impedance verticals. It's only 65 feet on its side, and look at its performance. It's only a couple of dB down from the very biggest antennas. So with only 4 elements, you can cover all the way around the compass. The main beam is broad. It's 100 degrees wide. So you won't get this amazing result that I described listening to a pile up from Europe and being able to hear the Northern Europeans on one beam heading and the Southern Europeans on the other. You won't get that with a 4-square, but you get great RDF, and the space requirement is really small. In order to get these numbers, you have to go from 1/10 of an acre to an acre or much more. Any other questions? Pete?
Suppression of common mode currents and pickup on the feed lines coming in. I've got about 500 feet from my receivers to the base of my It's our quad shield RG6 on the ground.
Yeah, I don't think you've got a big pickup problem, Pete. Now, what kind of antennas are you using?
Well, various times I use Beverage on the ground. I use phase P9AYs, which the deer kept taking down.
Yeah. Okay, so let me rephrase the question. Frank, you've been telling me about isolating feed lines, control cables for, let's say, for switching an array. Maybe the DC voltage going to a preamp. Are you really serious about this? For the loop antennas, the arrays using loops, whether it's K9AY, flags, all of those antennas produce low signal levels, and they are very, very susceptible to stray pickup from any other wires that are connected to that array. So for the case of any loop array, you have to be serious about this stuff, even if the wires are laying on the ground, because these arrays have low sensitivity and they depend on a high gain preamp and no stray pickup for their performance. On the other hand, for these short vertical antennas, those antennas have, well, the passive short verticals have very good signal level. So the passive verticals, 25 feet high with no preamp, if the feed lines are laying on the ground, isolation isn't a big deal because the signal from the antenna is far greater than anything you're going to be picking up from a feed line laying on the ground. For the active antenna, which has relatively small signal coming off that 25-foot vertical, feeding a high gain preamp, everything feeding that base of that high Z antenna should be well isolated. For the same reason, the signal coming off that non-resonant 25-foot vertical is very low, feeding that high gain preamp. So the high Z antenna also should pay attention to this same stuff. Okay? Next question, right here.
And given a choice between the lower RDF performing receive-only antennas and no receiving antenna, which is better?
In other words, well, what kind of a transmitting antenna are you comparing to? Just a vertical. Okay. Well, the answers are in the presentation, so let's take a look at it. It's right there. So if you've got a vertical, you're around 5 dB. So you can pick up 3 or 4 dB with some of these short, small antennas. And look at this small antenna, 65 feet on the side. I can pick up 7 dB of RDF in only 1/10 of an acre. So I think the answer is clear. Next question, right in front. Performance of a dipole as a receiving antenna on 160 for a couple of reasons. One, it's well known from people who've tried to use dipoles, even very high ones like WHAI's dipole at 320 feet, that the performance of dipoles for receiving is very poor. Why? Because it is widely believed that most signals that are being received on 160 have not necessarily from the States, but longer distance DX signals from Europe, from South America, that those signals are received primarily with vertical polarization. Not only with vertical, but primarily vertical. that doesn't affect the higher bands to any significant degree, but on 160 it's a big factor. So a dipole is a relatively poor receiving antenna because it's the wrong polarization. But let me answer your question, because you didn't ask that question, but I'm sure you had that in mind. A dipole is a poor choice. But a dipole definitely has RDF. In order to have an RDF of 0, you have to have an antenna that is truly omnidirectional in azimuth and elevation. And if you look at the pattern of a dipole, it's about 120 degrees wide with nulls off the end. So the RDF of a dipole is probably going to be, right around here, right around 5 dB. I've never computed it, but it'd be easy to compute.
And the other quick question is, you're mainly concentrating on 160 and 80. But if you have a lot of local RFI, say 20 meters, would then going to a receiving antenna in that case that would shield some of that be a good option?
Yes, perfectly good option.
Not the other ones, because then you said that would not be as good.
Yeah, and the signal levels on these, for example, let's go back to this array. Remember this array, in order to make it really simple, you remember how we matched this array to 75 ohms? We used a resistor. And why could we get away with that? Because we've got signal to burn on 160. We've got so much signal that if we're using a transmit antenna, we have to put an attenuator in front of our radio. So we have to throw signal away if we're using a transmit antenna. Well, if you go up to 20 meters, for example, we need a better receiver. So you're probably not going to like the idea of using a resistor to match the antenna on 20 meters. I think what you're going to wind up using is a transmitting style 4-square array on 20 meters. You can buy those. DX Engineering sells them. You can give your credit card to Tim. You'll have it Monday. But the 4-square transmitting antenna, it's made by it was originally made by Comtech, and it's still sold by that name. You can purchase that, and it's a pretty good receiving antenna. But some of the simplicity principles that we took advantage of on the low bands are not such good compromises once you get up to 20 meters. That you can't afford to give away that much signal. So think about the 4-square. Any other questions? Right here. Yeah. The loop arrays and the high Z 25-foot non-resonant vertical has very low signal levels. So you need a high gain preamp in the order of 20 dB or more to bring those signals levels up to acceptable levels. That's not a criticism of those antennas at all. It's easy to correct for their very low signal levels with a high gain preamp, but you have to do that for the non-resonant 25-foot verticals and for the loops. Any other questions? All the way in the back here. Okay, so the question is, okay, I'm going to put a very high gain amplifier on my loop. Am I going to have other problems from nearby strong signals? And the answer is yes. They're very susceptible to strong signals. And if you have that kind of a situation, it's wise to talk to the manufacturer first before investing a lot of money in it to tell him that he can tell you either it's going to perform well, you can tell him the distance of the broadcast station or whatever else. Yeah, that's a problem. It's a very clear advantage to the low impedance antennas is they are immune to this stuff. There's no active component in the low impedance version of this antenna. It has the disadvantage of having radials, but it has the clear advantage of no active component, so it has no susceptibility at all to nearby strong signals. So, if that's a real serious problem, you might think about a low impedance version rather than the high impedance one. Any other questions? Right here. Okay, Alan, does the power, if you look at the power poles within a few hundred feet, do they have ground wires running down the pole? Because that's the real problem.
One of
Yeah, because the real problem with the power line isn't the horizontal wires; it's the vertical wires that run down the pole. So you shouldn't. These high RDF arrays get their high RDF by careful attention to detail to get all the side lobes really low and to get the front lobe really narrow. And when you put these very high performance antennas near other objects, inevitably it degrades them, and all the effort you went through to get the high RDF numbers kind of goes out the window. So I would recommend that for any power line where there is a ground wire or any other wire going vertically down the pole, that you should, if you want to get these high RDF numbers, you should be at least a few hundred feet away from that pole to get the high RDF numbers. Now, I'll mention one more thing, and that is when you have switched the array so it's pointing away from that pole, so the pole is behind it, it's no problem. Because you're also going to discriminate from the re-radiation from that wire on the back of the array. But when you're pointing into that telephone pole with a vertical wire in front of it, any signals that are received by that vertical wire, and signals will be received and re-radiated, just like the parasitic element on your 20-meter beam, signals from other directions are going to get re-radiated into the main lobe of that high RDF array. So even if you can't get a couple hundred feet from that power line, you're still going to get the benefits when you point it away from the power line, but not when you point it into it. Yes?
Bill KC40, Frank, I'm intrigued by this vertical wire thing. I've got a beverage that just happens to be toward the northeast where there is a power pole. It's always been noisy stack. It's been greater than anything I've had receiving. But
yeah.
How much would I need to move it horizontally, parallel, if you will? A couple hundred feet would do it, you think?
How long is the beverage? Yeah, so it's on 160 meters. It's a great, that's 540-foot beverage is what I used as my primary receiving antenna on 160 for 20 years. Fabulous antenna. But you're pointed right at a power line. And it has a vertical wire running down. Yeah, so it's got all the really bad characteristics. So the beam width of a 540-foot beverage, the beam width of that antenna is roughly 60 degrees. So you have to move the antenna, just as if you had a Yagi, you have to move the antenna far enough so you're down on the side lobe of the beverage rather than foresighted right at it. And keeping in mind that a beverage has 60-degree beam width, maybe you could also change it so it's pointing further to the side. So you have to take advantage of the side lobe. Details are up to you. Any other questions? We ran out of questions and we're right on time. That's amazing. You guys did a great job. Thanks very much.